Okay, I'm going to try and do a demo of alpha beta pruning with this Minimax tree that we've got here. I expect that already you are familiar with these two functions, the max value function and the min value function. That's what I'm going to be using this whole time. I've kind of put as a summary along the right-hand side what each of these, the key values in the algorithm mean. The V value is going to be the best value that any particular node has seen so far from below, right? So it's kind of what it has experienced or its children have experienced. And it also always starts at negative infinity for max, because max is trying to get the highest score, so the best score it's seen is negative infinity. And it always starts at positive infinity for min, because again, min is shooting for the lowest score, so the best thing it's seen so far, if it hasn't seen anything yet, is positive infinity. Alpha, in contrast, is the best I've already explored along the path to the root. Alpha is passed down as a parameter, and then I can update alpha myself and pass it up as I learn more. And similarly, beta is the best sort of we've seen from the root. But anyway, what we're going to do is we are going to try and step through this algorithm, looking at alternately the max value and min value functions, which are the things that we're using, right? So when we call this function, we call it on a max node, and we will pass in for our max node, when we start this whole thing, we will pass in negative infinity for our alpha and positive infinity for our beta. That's just how we start this whole thing running, okay? And we will call max value. And so let's just look at what the max value code says. It says if this state is a terminal state, of course, we pass in three things. We pass in the state, so this guy, plus alpha and beta, which I filled in here. So if the state is a terminal node, well, it's not a terminal node, it's not a leaf. So then we say, okay, well, I'm going to set V to be negative infinity. Okay. And then for each of my children, so I have 3 children, I need to run this thing for each of the children. The first thing I need to do is I need to run this min value function on the child with my current alpha and beta. And then once I've done that for all 3, well, once I've done that for the first child, I will I'll compare the maximum of my current value of V and the minimum value that I get there. So let's run this function call right here, which means we're going to call min on the first child. I'm just going left to right because that's what I feel like, but you know, there may be some other arbitrary order. Anyway, so I am going to run the min value function now on this child. I'm passing in alpha and beta, so I just copy my alpha and beta from here. So my alpha is negative infinity. Oops, sorry. My alpha is negative infinity and my beta is positive infinity. Okay. And now let's look at the min function. The min function says you take a state plus the alpha and beta. Is this state a terminal state? No, it's not a leaf node. So V gets positive infinity because we're a min node, and min nodes are trying to get the worst score for max, right? We're playing the game against max. So we set V to be positive infinity. And then again, for each of our children, we have to do something. And in this case, for each of our children, we're going to compute the max value of the child with alpha and beta as the parameter. That's the first thing we need to do, and then we'll deal with this whole thing. So we got to figure out max of this first child with the same alpha and beta. So let's pass in alpha and beta, which are still negative infinity and positive infinity, all right? And then let's look at the code. So it says, is this a terminal node? No, it's not a terminal node. So make V be negative infinity because I am a max node. And so I am trying to, that's like what I've seen so far. The best I've seen so far for my V from my children or whatever is negative infinity because I'm a max node. I haven't seen anything yet. Okay, fine. So I'm still running my, and when I say that, the best I've seen so far, I'm trying to give you an intuition for this, right? What it really means is what it says in the code. It's just these comments here sort of kind of are how I think about it, right? It's a useful way to think about it. Anyway, we are in a max node. We are running the max value function. We've just set v to be negative infinity. And now it says for each of our children, well, start out by figuring out the min value of the child. So we're going to figure out the min value of this left child here. What you'll notice is since we're going to run min-val function on this terminal node, right, with alpha and beta turned in, but we don't really care what alpha and beta are because if it's a terminal, then you just return the utility of the state. So utility of this is 2. So we are just going to send back up the tree a 2. All right. And now we are back. We were in the middle of running max. It said first figure out the min value of the first child. And then figure out the maximum of my current v and the min value of that child. So my current v is negative infinity. The child was 2, and I compute the maximum of those 2 and assign it to v. So the maximum of 2 and negative infinity is in fact 2. So we'll get rid of that, and we will put a 2 in there for my v, right? Okay. And now the algorithm says, is v greater than or equal to beta? And 2 is not greater than or equal to plus infinity. And plus infinity is kind of the best that min has seen so far, right? So the best for min or the worst for max. Again, this is just trying to give you an intuition, these guys, of what these numbers mean. Anyway, so it's not greater than beta. So now we're going to say alpha gets the maximum of alpha and v. So let's see, alpha is negative infinity, v is 2. So we're going to change that alpha so that it now is 2. All right, so my alpha over here is 2. All right, and now if we look at the code, of course, we're looping for each child, so we need to do the same thing for the other children. So let's see, the next child is this 7. So we're going to compute we're going to run the min value function on that node. It is, of course, going to just return a 7, right? So I'm just going to kind of shoot that 7 back up. And now we're back in the max function. What do? We got the 7. And now what do we want to do? We want to take the max of 7 and v. So the max of 7 that we passed up and 2. Well, that's 7. And we're going to put that into v. So v is no longer 2. Now v is 7. I'm sorry, it's so messy, but there you go. All right, so now my v is 7. And now I am going to, let's see, what do we got? If v is greater or equal to beta, well, v7 is not greater than or equal to plus infinity, so we keep going. Alpha gets whatever's bigger, alpha or v. Alpha's 2, v is 7, so we're going to also update alpha, so alpha is now 7. Okay. And now we have to run this max algorithm for the third child, which is the 6. Of course, we run the min value function on it. It returns the 6. So we'll pass that 6 back up. And now it says, take the maximum of your v and whatever you got back. So we're going to take the maximum of 7 and 6. That's still 7, so we'll leave v alone. If v is greater or equal to beta, 7, still not greater or equal to plus infinity. Okay, so so alpha gets the maximum of alpha and v is 7 and alpha 7. So alpha is just going to stay as 7. All right, we finally looped through this for all 3 of the children. And so now we're going to return v. We're going to return that value v. So it looks like v is 7. So we are going to send up from this node a 7. I think I'm going to send things back up in red. So there you go. We're passing the 7 back. So we were actually running this min value function, right? And we were here. We computed the max value of the first child on the left. And the max value, it turns out, it returned a 7, right? So we're going to take, now this says take the minimum of whatever v is plus infinity, and the max value you sent back, so that's 7, right? And the minimum of plus infinity and 7 is actually 7. So we're going to change this plus infinity for v to be 7. Okay. And now the system says, is 7 less than or equal to alpha, 7 less than or equal to negative infinity? Nope. So beta gets the minimum of beta and v. Beta is plus infinity, and v is 7. So the minimum of plus infinity and 7 is 7. So let's stick a 7 in there next to beta. Okay. And now, hooray, we just did this loop for the first child, the left child. Now we got to do it again for the right child, right? So because it says for each child. So now we're going to, again, compute the max value of the next child node, this one, passing in alpha and beta from this guy. So alpha is negative infinity, beta is now 7. Okay. So I'm going to, let's see, I'll change colors. I don't know if you can see this, but so I'm going to put, let's see, alpha is negative infinity. Let's see if I can do that sideways a little bit more. And beta is 7. Okay. So where are we? We are running the max function on this guy, right? So it's not a terminal node. So v gets negative infinity. Fine. All right, good. Now, what does it say? It says, for each of our children do, and the first thing we got to do is compute, we got to run the min value function on the child. Well, this first child is in fact just a terminal node. So you and I both know at this point that it's just going to pass that 8 back. So let's not look too closely at the min code. You could, of course, look very closely at the min code. Pause the video and look at it, and you'll see that that 8 gets passed back up. Very good. So we got the first minimum value, which is 8. And v is going to get whatever's bigger, 8 or v. Well, v is negative infinity. So 8 seems bigger to me. So v is no longer negative infinity. V is now 8. Now, check this out. If v is greater than or equal to beta, let's see. 8 is, in fact, greater than or equal to beta. So what this tells us is forget about doing anything else in this function. Just stop the function, return v, right? Recursive function, fine. But, you know, it says do this for every child, but we're sort of quitting that and leaving and returning v. We're going to return this 8 up. So let me just write that in red so you can see it's being returned. And then, that's an 8, not an infinity. There you go. And let's just look at the logic of this for a minute. Why is it that I don't have to look at anything else in here? And the answer is that max here is going to do as best it can to get the best out of all of this stuff. And from min's point of view up here, right, or from max's sort of bird's eye view up here, if min has a choice of definitely getting a 7 or getting 8 or better, min's going to choose the 7 every time. So who cares what the rest of the stuff is in here, right? We can just, wonder if we can do a super, is there a shape that we can cool block out with? There you go. I'll use a star. I'm going to use a cool colored star. You're going to just love this. Hang on. So we can just prune, oops, that star's bigger than I thought it would be. I'll just put it there. We can prune this whole subtree, right? We don't have to look at this anymore. We don't have to look at those children. So where are we? We are just passing an 8 back up to this min node. So we were in here and we passed an 8 back from below. So now we look at this code and we say v is going to get the minimum of whatever it is right now and whatever we got from below. So the minimum of 7 and 8 is still 7, so we'll leave the v alone. And is v less than or equal to alpha? V less than or equal to negative? Nope. So the beta is going to get the minimum of beta and v. Well, it just stays alone. And we need to do this loop for each of the children, but we've done it for the left child, we've done it for the right child, so we're done. So now it just says return v. So we're going to send that 7 back up. So the 7 we send up here. Okay, so when we left this node, we were inside of the max value function, right? Because it's a max node. So, and we were just checking what's the min value of my left child, right? Min value of my left child is 7. So v is going to get the max of v, which is negative infinity, and 7. So v is going to be updated to be 7. So let's cross out v and make it a 7. All right. So we ran this thing. We did that. All right. Is v greater than or equal to beta? Beta is plus infinity. V is 7. Nope. So we can't jump out of this yet. We got to check out the other children. And so alpha is going to get the maximum of alpha and v. So alpha now is going to be 7, which tells us, I'll put the 7 on the left here, which tells us the best that we can do so far for this Minimax tree is 7, right? And that kind of makes sense. All right, so we are going to now do this max function because we're in a max node for the second child, right? What do we got to do? We got to compute the min value of the second child, passing in alpha and beta, though notice alpha is now 7 and beta is plus infinity. So let's get our pencil and let's put in alpha of 7 and beta of plus infinity, right? And if you're following along in the information on the left, right? Oh, well, let's do, we're doing a min node. So let's do the first line here, v is positive infinity. Then what do these values mean again? Well, here we've got v as positive infinity is the best that this node has seen kind of from below almost, right? Is positive infinity hasn't seen anything good yet because it's a min node. It wants to see low numbers. Alpha is the best option along the path to the parent, right? So far, as far as max is concerned, alpha is 7 is the best thing, right? That's come along that will make max as happy as possible. Beta is the best thing that's come along that will make min as happy as possible. And right now, that's plus infinity. Pretty yucky, but there you go. Right? Beta wants something real low so that max will lose big points. Okay, so we are in here. We have set, it's a min node. We've set v. Now we need to do something for each of the children in here, right? So what do we got to do? Well, let's see. First we do it, we're going to run max value on this left child. So we're going to pass in alpha and beta, and we're going to run it on this node. So alpha is 7 and beta is plus infinity. So let's just copy those down there. So alpha is 7, beta is positive infinity. Okay. And now, excuse me, let's run max on that node. So max says, is it a terminal node? No, so v gets negative infinity. Fair enough. Okay. And now we need to get the min value of, for each of the children, we need to get the min value of each of the children and do this whole stuff. So let's get the min value of the left child. Oh, that's just 4. So we're going to pass it back up because if we run min value on that, it's a terminal node. So we get that 4 back. And now we ran min value, we got a 4 back, and we compare 4 with v. Well, v is negative infinity. We're a max node, and 4 is definitely better than negative infinity, so let's update v so that it is now 4. Oops, I don't want to do that in red. So v is now going to be 4. Okay, fantastic. And what's the code say to do? V gets to the max. Okay, if v is greater than or equal to beta, no, 4 is not greater than plus infinity. So alpha is going to get whatever's bigger, alpha, which is 7, or 4. Well, alpha is still bigger than 4, so we'll just stick with that alpha of 7 right now. Okay. And let's see, let's keep going. Take the next child. This is the next child. It's a terminal node, so I'm not going to go through the whole code with you. I'm just going to say the 5 gets passed back up. Okay, so that 5 gets passed back up. And now we have to take the maximum of the 5 that came back up and V. Well, let's see, V is 4 and 5 is bigger. So let's update V. Oops, to be that 5. Cross that out and V is now 5. And is V greater than beta? Nope. So alpha gets whatever's bigger, alpha or V. Alpha right now is 7. So 7 is actually the best Max can do so far, right? Because Max can go vizhoop and then Min will go that way, and so Max will get the 7. So 7 is not, or 5 is not better than 7. So we're just going to leave. We're going to leave the alpha alone, and now we have just run this max function for both of the children. So we're going to return V. Looks like V is 5. So let's do that in red just so it's sort of kind of clear. We're going to send a 5 back up that away. Okay. So we're sending a 5 back up that away to the min node. Let's go back and see what was going on in the min function. We computed the max on the left is 5. Our V is plus infinity. So the minimum of 5 and plus infinity is 5. So we will update that V to be 5. Okay. And let's see. We updated V. So now is V less than or equal to alpha? 5 less than or equal to alpha. Oh, yeah, it is. In practical terms, that means Min knows at this point that if it picks the left child, it's going to pick a 5. But that means that since Max knows that with everybody playing nicely on the left here, it could get a 7, Max isn't going to go down this way. That's stupid. So the code tells us if V is less than or equal to alpha, then just return V. So we're just going to return this 5, and we're going to chop off this child with all of its child nodes. So let's get that cute graph again. Where's the picture thing? And we are just going to prune the whole right side. Oops, the whole right side here. We just don't need to look at this stuff anymore because we are returning the V, right? I'm drawing these stars on here so you can look at this at the very end and say, hey, what did we prune? And you can try it again without all this, if you want to just copy the picture. But really what happens is the system just says, okay, return V up here. Forget it. Don't look at this child. Don't look at its children. All right, so we are going to return the 5 back up here, okay? So this guy is running max. We just computed this min value thing here, right? And that min value was a 5, and we say, what's better, the 7 or the 5? Get the max of that, and it is still the 7. Is V greater than or equal to beta? Well, beta is still positive infinity, so no, not better. All right. So alpha gets whatever's bigger, alpha or V, and alpha is 7 and V is 7. So we leave it alone. All right. That was child number 2 of the max node at the root, right? That was this child. So now we got to do this one again. We're almost there. So let's see what happens here. So we are going to figure out the min value function. We're going to run min value function on this node with the alpha and beta passed down. So let's see, alpha is 7 and beta is still plus infinity, right? So we are good to go. And now let's see, what do we have to do? It says for each of the children here, we have to, oops, sorry, no. Is this a terminal state? No. V gets positive infinity, so V is going to equal positive infinity. Very good. And then for each of the children, V gets the minimum of this. So we got to get the max value of the first child, which is 9, so it's just going to pass back a 9. So V is going to get the minimum of the 9 that we passed back up. And V is plus 1,000, so, or plus infinity, sorry. So 9 is smaller than that. And then we say, is V less than or equal to alpha? Well, V is not less than or equal to alpha. So we have to, we can't just do the quick run away. Beta gets the minimum of beta and V. Well, beta right now is positive infinity. We can do better than that. So now beta is 9, right? So we just finished this loop for the left child. Now we're going to do it for the right child. And we say V gets the minimum of this yuck. Oh, we got to compute the max value of the right child. So we're going to run max on this guy. And we're passing in, well, C is that node, and alpha and beta. So we got to copy down the 7 and the 9 down here. So alpha is 7, beta is 9. Okay. And what do we got here? We're in a max node. So we're going to run this function, and V is going to get negative infinity. All right. And then for each of this one's children, we are going to check out the left side and then the right side, right? For each of these one's children, we're going to run the min value function on. We know this is just going to give us a 13, right? So let's just keep going. We're going to get 13 back versus V, which is negative infinity. The bigger one of that is 13. So our V is going to change to 13. And, oops, sorry. And is V greater than or equal to beta? Let's see. We've got a 13 so far on this max node, and that is in fact greater than or equal to beta. So this is going to tell us you can just return V. Because look at this. Max might, we don't know what's in this 12, right? We might not have seen the 12 yet. Well, we haven't seen the 12 yet, right? But without seeing this 12, we know that min is never going to pick this branch because the 9 branch, at least, doesn't let max pick a 13. And if this 12 is smaller than 13, max isn't going to pick it. And if this is 155, max will pick that, which will be even better than 13, better than 9. So we're just in this inside of this min node. Since V is greater than or equal to B, we're just going to return V right away. So let me, just because it's nice to be able to see what did we dump, I'm going to say, all right, we didn't actually look at that right child there, right? And we're going to return V, which is 13. Yes. So we'll send that 13 going back up. And now we are in this min node. And so we got the value, and V is going to get the minimum of the current V and what we pass up, which is 13. So we're going to leave it alone at 9, right? Is V less than or equal to alpha? No. So beta is going to get the minimum of beta and V. Beta is still 9. And we've explored all the children. So now it's time to return V, and V is 9. So we are going to return that 9 back up. Okay. And we're back into our max function, right? Which says, okay, I was checking the child, up came a 9. V is going to get the maximum of whatever V is right now, and this 9, oh, hey, that's a better route for me. So V is going to get, let's cross it out and make that 9. And is V greater than or equal to beta? No. So alpha is going to get the maximum of alpha and V. So we're going to change this guy. Alpha is no longer 7. Let's put it there. Alpha is 9. And miracle of miracles, we're done everything. And what does this 9 tell us? It tells us, now it tells us that the best value that we can get for this tree is 9, right? So in fact, the path that we would want to take, if we took a path, come on, let's make that a nice highlighter. Let's see if this works, is the path to the 9, right? So this, ooh, look, that almost works, right? So this path here is the winning path. It's going to give us our best value. Notice the algorithm, this particular algorithm doesn't actually tell us what the best path is, right? The algorithm in our textbook gives us is a function that returns both the path and the best value to take. So in some sense, that's a better algorithm. On the other hand, this algorithm, I mean, they're very close. They're almost the same. This algorithm, on the other hand, lets us just concentrate on the max and the min functions. And this implementation is from Russell and Norwig. It's from sort of a classic textbook in AI, which is a really fantastic textbook that you might want to take a look at. But it's quite an expensive textbook, so we're not using that in our class this semester. Anyway, so that's alpha beta pruning on this tree. If I asked you what nodes get pruned, then you would say, well, that whole branch gets pruned, right? And that whole branch gets pruned, and that one, because we never looked at those values, right? We just ignored them and kept going, right? So remember, why are we doing all of this? Well, we had some nice ways to prune when we were doing our single agent search, right? We had the multipath pruning. But now that we've got a game where we're playing an adversary, we needed a new approach to pruning. So that's what we're doing now. Okay.